code panel. We will start with each panel member presenting a 3-minute presentation, and then we'll start with some economy questions that we have prepared for the panel, and then audience can ask the questions. So a little bit of introduction to the panel member. We have Lian Tran from Fermi Labs, doing a lot of particle physics stuff and doing a lot of embedded AI, targeting FPGAs. We have Ryan Kastner from UCSD, doing a lot of very different kind of domains. We have Gabe Hayes from AFD, doing a lot of ML on FPGAs, on GPUs, on AI engine. We have Shifan doing CAD stuff. We have Sunafani doing a lot of HPC and some other domain for FPGAs. Okay, so Ian, you want to start?
So yeah, I'm a particle physicist by training, and this is the experiment that I grew up on. So you'll see this experiment in the Hadron Collider. It's a very, very high rate and high energy particle physics experiment. The massive data rate, so 10 billion collisions a second, 10 petabytes of data per second. So it's a very complicated data processing chain with lots of different steps to be able to reduce the data to something somewhat reasonable. And there's a whole FPGA filter farm that's in there that's doing the first level of data processing. And then we've also explored FPGAs in other areas on the sort of more for processing and acceleration. And just to give you a flavor of the things that we do, this is a very complex multi-tiered system, and these are a few of the designs that we have on these different filtering systems, because it's a lot of different camera systems all that have to be integrated together. So I just want to say, like, from a FPGA usage point of view, I mean, these are domain-specific algorithms, they're machine learning algorithms, and these designs are a mixture of RTL and HLS, so it's really kind of all those areas. So yeah, so as in my work, I've kind of branched out, I guess, into different areas of science as well. So this is a fun picture that also poster Ben talked to you about it. And just talking about how the world of physics maybe is colliding with other experiments in chemistry or quantum, quantum, neuroscience, fusion, and so on. And so here's this is the sort of pitch for embedded streaming real-time applications, where the computation times could be milliseconds, but they can be nanoseconds. The data rates are terabytes, megabytes per second, depending on the sensor type. And so the vision, why does this have to be so fast? Right? I mean, you have inference at the scale of nature, at the scale of experiments themselves, right? So scientific instrumentation, diagnostics. They come to an FPGA, let's say, a control agent, and you have to do actuation of decisions. And you don't have time to just do it later, right? These are things that you're trying to control, natural systems at these scales. So I saw James's talk, I guess, was input dependent irregular streaming data analytics, which is a lot of what we do, right? So all streaming applications, and they go far beyond the applications that are maybe in industry or there are some of them we already talked about. Okay, so maybe onto the one picture. This is actually something I'm not a plasma physicist, but through our work, we've kind of run into other groups, and so this is an example of a camera on 1,000,000-degree plasma that has to then control this plasma to different modalities, both in the amplitude and phase. You can see this with the high-speed camera sees, and actually the most interesting thing is actually the clock running at the bottom, where I've been talking forever and about milliseconds passed, right? So these are the types of application streaming video applications that are these different things. All right, so let me get on to what the panel questions. Maybe what I want to convince you is actually that scientific applications aren't that different from a lot of the other real-time domain applications that we've been talking about. So while maybe the context seems very different, some of the challenges are very similar. Programmability, which people talk a lot about, we use a lot of HLS, so synthesis times and the challenge there also similar. One thing that people have explored recently is also the idea of streaming with PL and AIs together. But the main messages I wanted to say are that applications are bespoke, right? You have all different types of representations, custom numeric formats, time series, irregular sparse images, point clouds, whatever, all different tasks, and all different types of constraints from nanoseconds to milliseconds, GHI certification. But the main point is from our domain side, I guess, is that we're mostly domain scientists, not FPGA experts, and we also don't have the economy of market scale. Right? These are all maybe one-off experiments, or maybe 100 labs in the world have these things. If we're one of them. So just as important, open source is important, community support is important for us. The word we use really user and application driven. I always say that some applications is infinitely better than no application. People that aren't even aware that you can do these sorts of things, certainly make the world to that. And then of course accessibility, usability is super important when you're not FPGA engineers and experts. So it's this additional sort of flow, which we really start with Jupyter, get all the way to the end of the So I don't know if I'm doing this right.
Thanks, yeah. Our next speaker is Brian Kafner.
All right, so I am putting my security hat on right now. So I'm going to, my title is, Are You the Master of the Domain? This is a reference to Seinfeld episode from more than 30 years ago. I won't maybe talk about what that means necessarily, but that's what it came to domain security, right? And so we're going to talk about that. Cool. I'll get into my slide. This fast. Okay, this is a great cartoon by Randall Monroe. So talking about modern tech stack and about how security plays a role in pretty much every part of that tech stack can be hacked. And that's a big part of security. Security is main is that security researchers are white and white hat, black hat, all these red hats, different things, and they're all very suspicious and kind of shifty and maybe shady in some sense. That's good people. But security can be done anywhere. I think in FPGA world we care more about the lower end of that stack, and this mouse over about right. So it's like I feel real bad for those nation-state hackers who spend years implementing and cultivating some great hardware exploit, don't even start their entire databases, audience goes. And that's pretty true for security things, right? So, going maybe a little more specific in FPGA land. Steve Trepberger, who I miss seeing around these conferences, one of the earliest Silence employees, came out a couple decades ago when Jason Moore was also a security researcher in Silence and said, our customers really care about the bitstream of the IP, and so we should print this. And did some great work, and then this jerk Christoph Farr came along and figured out how to reverse engineer. So that doesn't work, right? In fact, Steve told me, Christoph ruined security engineer or FPGA security funding for the community for quite some time. Nice, Christoph. So look at this young guy, maybe 20 years ago here, actually right here next door at the Naval Postgraduate School. We had some very early on research about how do you make sure that FPGAs were secure. So some of the earliest NSF-funded hardware security researcher was some great security researchers, Cynthia Irvine, Tim Nguyen, and Tim Sherwood, program high for many, many years. So we came out with this idea, can we protect the IP cores and make sure that they're safe? And man, look at all these jerks that came out and said, no, you can't. It's a big X over there. Are you the master of your domain? Are you the king of your county, the lord of your man, the queen of your castle? No, you are not. I have to guarantee you that that's not the case. So how can we make this better? So a lot of the work I do right now is in verification. So I've switched from being an attacker to a verifier. We have a great security researcher in our department. His name is Stefan Savage. He's hacked cars. He's hacked all kinds of different things. He's hacked Bitcoins. He's hacked drug smugglers. He's hacked anything if you want to hack. And I say, Stefan, your job is so easy. You can just break things. How do you fix things, right? So I've been trying to fix things for a long time in security, and that's a hard problem. Here's kind of what we do. A lot of the hardware security, especially, is obfuscation. So we just don't talk about it and don't attack it. Is really bad as security researchers. That's not a good thing. Sometimes we do proof by intimidation. Is like, how dare this is kind of maybe the Trenberg corollary, right? You know, if you attack my system again, I'm never going to fund you, right? So don't you dare, right? Do this thing, or else we'll be in big trouble. We like to do a lot of proof by hand waving. That's a really good academic exercise. And a lot of what I see, I work with a lot of companies, is this proof by exhaustion. It's like, the ship something, right, at some point, and you make a best effort at trying to make it secure. But at the end of the day, it's not going to be secure. Nothing is ever secure. And the last one, which is one of my favorite one, is proof by citing high identity. So I asked a very famous hardware researcher many years ago. I said, they were building a secure architecture. I said, have you done any verification on this? How do you prove this? I said, well, that's a very philosophical, that's a very religious question. So we never answered it. So maybe what are some solutions here? I think open silicon is one of the good solutions. And people come to me and say, right, does that make it easier to attack? It's all open, right? But I think that's definitely not what we want. There's a idea called Kirchhoff's principles that you want to make sure that things are open, right? So there's really some great examples recently called OpenTitan and Calyptra, doing hardware root of trust, open source, totally open, and those designs are very secure, in my opinion, probably more secure than all closed source stuff that is being developed in companies. So I think that's a really great solution that should be pushing, and hardware has become it. So I'll end with that, and I'm happy to questions. So,
Thanks, Ryan. The next speaker is Gabe Ways from Italy.
Hi, everyone. So the context for this talk is brainwave, which you heard a lot about on Thursday, so I took it down to what's on here. But just to recap a little bit, brainwave is an FPGA-based accelerator used in data centers for giving neural network inference. And so there's many high-level applications that go on top of this. But the basics of this one is that we built call it a processor or runtime programmable overlay for inference, where you had different functional units. You had a program that ran on it for each network, so that's how it was implemented. And you had different numerical formats that we used throughout the processor that was figured when you compiled it. And that was really neat because in FPGA you can design your own number formats and you can actually print them fast and operations of the cycles. So unrolling pipeline crazy. And so when you're mapping these things to FPGAs, you need all the LUTs you can get. You need everything. LUTs, VRAMs, you have huge numbers of weights and activations, so lots of numbers that you need to process and store and implement. And then you have DSPs, so if you're using standard formats, you can use DSPs and help. If you're doing your own number formats and few enough bits, you can map them really efficiently with a couple of LUTs too. And then you need as much memory as you can get. You need as much communications as you can get, either PCI or networking. We're fortunate enough, we have fortunate to have the catapult FPGAs, so we have this framework that's secure. So on top of that. And so, but overall, you have both basic pieces. Programming. Anything you need to do, we just import it. Both compute, storage, application, even better tools. So my wish list is probably what anybody uses. ones, right? Just giant devices, or LUTs, hard compute units that you use using standard types of hard units that you can fast on chips. And one of the things that was a big problem for us was data distribution. We had a lot of data that had to be recyclable, and then we would have to sometimes do manual fork and planning and stuff to meet. We had high speed, meters, 5 millimeters, really as fast as well. So it was just hard to get that off for. So we want the data distribution, crossbars, just everything. That's PCI. And we also want everything to be really cheap, right? Because that way it's more. So we want everything. So in order to do that, you need to sell tons of them. To make these things bigger, there's more power, more food to deal with. Right? So there are trade-offs here. Hopefully.
Thanks, Kate. Our next speaker is Suhaib.
So I'm not proper HPC yet, but I'm trying to use it, which is HPC because of going down because of HPC activity. So over the last couple of years, through various collaborations, we've been looking at things like stencil codes and solvers, word processing, large-scale simulation. Basically, applications that have huge amounts of parallelism, particularly run very large machines with many GPUs. And what we want to try and explore is whether we can make a dent somehow in that. There are a few things that help us do this. Obviously, the fabric of the FPGAs has been increasing in performance and density in terms of operations. Millimeter is something that has been very useful. The fact that we can build those data flow pipelines on chip, and that we can do the custom data types and sort of build things that are optimized for a domain. I think the HPC community is recognizing the importance of data types and narrow data representation. And I'll mention that in a bit. One of the key things that has allowed, I think, a lot of the work that people have been doing on a lot of the HLS frameworks and just the use of FPGAs using HLS has been the abstracted host interface that we've had with things like the Vitus Flow, right? And that's why the 280 now seems to be the de facto standard. And bad news, the 80 will not be that if no one is giving us that same thing. So I think this is just a call to the people in designing, and I think Altera is doing a good job of saying that. But we have sort of settled on the U280 because of that. It's been very easy to have students start working on something, build the hardware, and then have the host abstracted and give us that for the V80, and then sort of just sit there and show us. Unfortunately, we bought two. So I think those high-level synthesis flows have been much better recently, and that's something that we are seeing to the extent of productivity and the capability of exploring in design space and actually finding a point that you wouldn't have found in RTL design. That's the important thing. Is yes, the ultimate RTL design for a particular point that you are also exploring in HLS might be better, but you've got to find that point, and that's not always easy to do. Of course, number one, build times. Build times is a huge problem. When we try and explain this to people who are not from the FPGA space, they sort of scratch their head and don't understand how this is possible. I have a pet peeve that I've been exploring for the last 10 years, which is somewhere in AMD and Intel. There are these great silicon engineers who are sitting there spending hours of months, years of time optimizing their DSP blocks to run at 750 megahertz. And then we will sit there and say, I've achieved 300 megahertz for my design. That's a huge problem because we're leaving a significant amount of performance on the table, which the architecture is capable of, right? But just by virtue of the horrible flows and RTL as the sort of the IMR and things like that. We're not getting performance. And when we're sort of at the 1.1 with the GPU, that extra frequency would easily push us well over what we need to do. I think the sort of scaling beyond a single board, I think we all see all the papers that say, yeah, we've got this great thing that runs on a board compared to one GPU. No one's running serious workload on one GPU. So we've got to find a solution to scaling it to larger issues. And we have the secret weapon, which is sort of this ability to directly ingest and pass data to from FPGAs through high-speed network interfaces or even custom things, which GPUs have to some extent in those DGX boxes, but those are things that could give us tool. I don't know what it is with FPGA tools, right? So, you've got this cool design in Vitus HLS 2019. A couple of years later, you've got something and you want to compare it, and it doesn't work, right? And you can't convince it to compile. There's no way to fix that. You've got to run an old machine with the old version of the tools, with the old version of the XRT and shell, just to be able to get something up and running. I think that's a huge issue that just kills the productivity and means that people are rather likely to use. There are also a number of boards that just miss any instrumentation that allows to get the power measurements and various other things that would help us prove point. And I understand it's not always clear in production. And then we also have, I think, a challenge that some people have been trying to address, which is that we can't just look at our chip as this homogeneous state. Once you start having an HBM and DDR and Ethernet in different places on the chip, then it's not as easy as we like to claim. Now, I think that the challenge, and I saw this in earlier research with PR, is that we've sold FPGAs as this great thing where you can write some code, compile, and it will work, right? But the reality is there is some physical consideration underneath, and we haven't yet found a way to abstract that suitably for designers. So we need a way that we can capture the important characteristics of that physical limitation and allow that to be exposed in a way that designers can exploit that, but without having to get into the details. So PR is a good example, because PR is great, but you've got to also be a physical designer to be able to do that regions. So I think that's something that's also sort of being very simple. So thinking about moving forward, I think one of the key things is please do not kill flows that have become established and then try and force everyone back into an RTL world if you want your devices to be used as HPC circuits. One of the things that we have to be very careful about is we've been winning a lot, or claiming to win, because of custom data types and narrow number of presentations. GPUs can do that now, and they can do that better than we can, right? Because their operators are fracturable on a per kernel basis without any sort of reconfiguration. We do have some fracturability and some decodability, but that's always on a per configuration basis. It's not, you can't use the same functional unit in many different ways from one iteration to the next. I think that's something that needs to be addressed if we want to stay, because the GPUs are now running at PFP4s. In fact, we'll probably see that the sales pitch on the latest GPUs was only claiming the throughput at 4, right? And there was no improvement at the 8 or 16. I do think coarser granularity will give us an edge at some point. I understand that's not always easy to decide what that is. I think scaling up is something that we have to try and address in community through the frameworks and the programming paradigms, including doing away with it. You need to start thinking about that strength of the and then finally, I think the point was made yesterday as well, that reconfiguration capability is still something that while we're using it for single context over compiled thing, I think there's a lot of room for how we're going to take advantage. And if you're interested in work like C, you've got as much to discuss stuff.
Thank you very much to our speaker. Next speaker is Shrikant. Hello everyone. So not only talking about some of the ways FPGAs we're doing at FFX. I'm not talking about the foundational technology behind it, some focus of the FPGA and the tools we can use. So if you think about yesterday, I start architecture and FPGA architecture study like 10 years ago. When we have some new idea in the mind and want to prototype some new FPGA architecture that's happened. And we realized how many industrial leaders can do that. And you just hire a large team of hardware engineer and software engineer. Hopefully in 1 year or 2, you will have some tape out. You hope it will work. But nowadays, what we have done is like we can take out any FPGA architecture very customized, and with the open source tool and the mix of open source tool and commercial tools together, and the team size will keep under 10%. And if you want to iterate the layout, it's less than 24 hours. If you want to do a takeout, in our experience, shows that all the layouts we see on the right side of this slide takes like 6 months to take out and validate that. And in that case, you see that we have built a lot of open source tools and with the community together. And in the hardware development, when you want to develop your FPGA layout, from the FPGA architecture description language, you can customize FPGA and run the flow. All the tools you see here in the TDK, and some of them are open source already, like Skywater. And all the hardware flow, like message generation, circuit design verification, physical layout generation, you can already find open source tools to do that. Also, you don't need to stop your software development while you're developing hardware. We have all open source tools together, and you can start evaluate your FPGA architecture at both hardware and software level. And you can generate district before you tape out and evaluate if the application needs a FPGA target or not. If not, you can reiterate again very fast. And the core of this tool chain is like it's called open source framework, FPGA framework. As details shows on the figure on the right side. It's a fully modularized modern code base, integrating quite a number of open source tools together. And we can allow you to customize any FPGA architecture you like. And also, it's a multifunctional and single objective framework where you can implement one flow. It's called chip design flow, which converts your FPGA architecture to your physical layout. Another flow is more like we call end user design flow. In that, when you try to use your FPGA or your virtual FPGA, you can benchmark your FPGA architecture by converting your application Verilog into the district. Our PV system can help you to put your FPGA layout or FPGA netlist, fabric netlist together with the district and run simulation. And you can validate your FPGA PPA before it goes on tape-out. And on the left side, we show that we have already enriched silicon tools, and the video shows a very simple guideline or tutorial on how to use the RapidFlex software, which is based on OpenFPGA framework. And feel free to visit our GitHub and documentation. All the OpenFPGA part is open source, and we'll talk to you. Thank you very much.
Okay, so the next we are going to talk about some questions to our panel members, and also we have some domain experts in the audience. We have James, text analytics. We have Big Brown doing HPC on FPGA, the data engines. We have Henry Putnam sitting there at the back. So networking related questions you can ask. So we have a bunch of domain experts. So please feel free to ask questions. So let's maybe start with some of the basic questions here. So the first one, can you or how do you plan to take advantage of new FPGA features in your domain, right? And those FPGA features could be something like hardened NOC or
bigger and better memories like URAM or dense compute like AI engine. So maybe let's start with anyone. Yeah, maybe.
Yeah, all of these things are things that I was talking about. We did see that here for what pretty much design.
So if you had to redesign brainwave gate, taking advantage of maybe AI engines, what would you do? Right? Like,
So a lot of thinking when it comes to AI engines with seven. That and there's such a complicated that a soft processor is or a soft processor and often commonly at the time everything is parallel. We still want to third that we try HOS for at least the modules. And then how specialized specialized I think we still do some less. Something else, especially one both hard body for us.
thank you very much. Maybe one question to you, James, about using log uh, in text analytics and those kind of applications. How do you plan to like? What do you see the advantage of log? Those kind of things, right? They've asked the question afterwards. I think it's broader than right. So I think if you want to be support async networks, you need wires. And I work in computing. And in computing, things are much more structured. And so this kind of fit with like back then when LC showed out recent what Bill Galley said is that route data don't out fine. So I think a lot of computing applications, once you migrate, once you move there, then it makes a lot of sense to move data. I don't care how different it gets there. And we can design things to cater to the latency consideration. And also I think when you look at SOCs, there's a lot of axiom. Once you hit the axiom, you are making some mistakes. And so I think if the figure, design get figure, use architecture and modularity, if they all come to choice, I don't think we can get away from it. So these things could get away because we get figured out. We have to do it. I don't think we can be stopped. So my question is a little bit out top. Well, not these. Should ask later or ask it?
No, it's fine.
So there's one thing I didn't hear is so on my probably was a Chemlock. So he specializes in embedded FPGA, something that goes into an SoC. And he does an RTL, he does it with async flow. And it's quite good, like as good as center cell gate. But it's that good. Okay. And so in that environment, you can imagine, right? You can specialize all you want. Right? It's all RTL outcome. So if he actually he also started with VR, you can throw whatever you want into it and all pass it to basic flow. And so I think so one of the things we can also think about is so it's not FPGA because it's discrete form, in these embedded usages. Maybe it's not there, you have a lot of it's not one thing to even special. So I think I'd like to throw that out there. That wasn't a question. I just want to bring it up. Yeah. if you think about the embedded FPGA technology that mentioned, so Reflex is offering this embedded FPGA technology, the EPA platform now, right? So when we think about that, so the FPGA is part of your ASIC. You can do any domestic task you want. If you think about the history of FPGA industry, what we have explored is like inside an ASIC or any SoC, the FPGA can do very critical tasks you want, which can be highly confidential sometimes. And if you see that NYU has a number of papers talk about the reduction and some critical function, mathematic functions can be done on the FPGA to prevent people to hack it. Because even so many companies, they can reverse engineer FPGA, not reverse engineer ASIC. When you go back with an FPGA, without any stream of any knowledge, especially when you do like modern FPGA technology, it's standard based. It's very hard to crack them. So that's why it creates more. It can help on the security issues, and also when we do something like runtime tasks, when we think about you have 20 different types of workloads to run on your ASIC or your SoC, and people will think about FPGA. Because if you just want to do your ASIC, you have to duplicate your model like 20 times. Each of them have different features together, and just increase a lot of your life cycle. You may have a big team to handle these 20 different blocks, starting from RTL, verification, PT, and sign off together. Why not just do an FPGA? Somehow it can be very simple, and you can increase the life cycle of the SoC then. Because in all the basic it's not right. If a new workload is not working, it's not working. But you have FPGA, you have the possibility. And sometimes, think about some encryption standards where they involves or coverage protocols involves serving as encryption engine or I/O through logic. Somehow, FPGA can give you a longer life cycle of your SoC, and thus FPGA is only yours, not ours, right? When you FPGA, and no one is going to do what you're doing on the FPGA. Just deliver to your customer.
You can use that mic, by the way. This is true.
On one question, line, on the IP security. The two questions. Number one is, so recently you have on FPGA you have SRAM based, you have normal based. So the normal based on the higher security, also one stop. So the second question is how to stay connected and I was wondering why would you higher security protection?
Yeah, sure. So I think maybe a comment on the eFPGA, but also on the first question is that they're more secure, but still not secure. So an attacker with enough resources will be able to figure out your design from the FPGA. There's some people in the middle of the room that are doing nice projects on BTI effects to certain level of instruments. And so certainly it's going to be probably harder, and I understand why DoD and other government agencies are pushing behind the FPGAs, but that stuff is still not secure. Or computing, anything that computes will give out some information. It's physics. It's physics. So I think it'll be harder for that because you're now putting in, not externally, and you're not worrying about encryption and these sort of things like you're saying for extra types of stuff. So it's not as easy to grab. But I still think it's possible for patient state level 2, level 3 sort of attacker. The second part was on ClipTrail or OpenType. So if you look at those, so you can look at all of that stuff, right? You can look at all of that RTL. You can look at, and then they have a really outstanding set of verification that they do. So they have test benches that they go through. They have all kinds of history of, we found a flaw in it. We tell them there's a flaw in it. They fix the flaw, right? So it's got a lot more eyes on it for many companies. then a design will have that is closed, right? So I work with, for instance, Intel, and I think Intel does an amazing job on doing hardware security stuff. But they have 100, 200 security researchers there that do a great job. But if you have stuff in OpenTitan and Calyptra, you now have those people, and you also have hundreds, thousands of other people in academics who are looking to break things. And we'll tell you when they break things. That's what we like to do, especially as academics. We like to break it, we like to polish up it. And then you can fix it, right? So I think that's why it's a lot more open. And then they have all these fixes, right? They think about side channel stuff there. They think about all of these sort of problems, and it's in there. Right? There's flows in there on OpenTitan, for instance, that I think makes it a lot more secure. So that's why I think it ultimately will be better.
Questions? Do we have any questions? We are building, let's say, a network specific FPGAs. What kind of
Yeah, so the evolution of our kind of networking infrastructure at FPGAs, we've ended up really pulling in more and more processing power close to the FPGA. And that's been partially just to, wait around for PCIe, it's a processor, but a lot of it's also been about security. We're trying to physically isolate VMs that are running server from the VMs that are running our hypervisor code. And so it's kind of a spectrum meltdown kind of thing. So if you're physically on different cores, you don't have to worry about a lot of it. So security does have a big impact on what we want. So a lot of what I'm finding is do you want some kind of interesting processor complex on there? Ones that they have so far that look good to be like 8 microservices is not enough. They also don't blow a bunch of stuff, a bunch of power. On server class processor that have just across the sky. The other piece that I find that where people are specializing was they just want to throw in every piece of hard logic they can. But one thing you have to consider is it's a wonderful idea. Let's just put all the stuff in the periphery, chiplets on the side, and we'll just add anything. Or maybe you can actually just take regular things and throw FPGA on the side in the future. The problem with those approaches generally if you have a bunch of hardware logic and then it has to pass off to the FPGA, you don't have a way to kind of catch up with the data it's doing if it's coming in first with a hard logic, then it's off the end. When first comes the FPGA, you catch up all of that logic, feed what the ASIC is expecting, and then come back out. And so there's those two different ways, but they are very different. People seem very similar. The other piece is you're just putting chiplets all over the place, and you're having data moving to the LUTs, but then they have to move on to a chiplet, back to the LUTs, then onto the chiplet, back to the LUTs. You have a huge problem in terms of where the data is, size, how much data there is. You can say that the NOM helps, and certainly does in that sense, but then you start using all of the NOM bandwidth moving back and forth with the chiplets. So the more and more you can integrate things to the fabric, things like clock rates, SPs are integrated to the fabric, or not. I think the fabric is related to those. I think the more successful you're going to be in terms of integrating that kind of
maybe next question. So we have been doing a lot of HPC stencil solvers, trying to run them on FPGA. So what is your experience? Do we have enough HBM bandwidth on our devices? Are you able to take advantage of the full bandwidth? What are we limited? Do we have enough ASP configured? Like, what are your thoughts?
So I think that the cell architecture of the DSP plus FPGA data center, when you differences in the DSP, that's a dramatic improvement. But there isn't a data center form factor card that works in lightest that has that in HBM. So we're sort of stuck in this mishmash of platforms and support tools to be able to demonstrate. But the experiments we've done, sort of ISFPGA25, which is retired, right? But that's a much smaller and doesn't have HBA. We also have that same problem working with the air engines, which is there is no engine device. So I feel like there are lots of pieces that make a lot of sense. The big picture sort of progression of the platform as the HPC accelerator is suffering because of various boxes that have been ticked in various areas. But they're all moving in the right direction. The AI is very useful in terms of that ability to spatially build in overlays, but we can't feed them enough value. HBMs and UDSPs are very, very useful. But again, we don't have the fabric of the huge number of things to demonstrate in volume.
I mean, I think the elephant in the room is like the tools just everywhere. I'll go over to you in a little bit, but that's always the problem. They've got these powerful features, and it's just an enormous pain in the ass to get into running on these things. And I think you can talk a lot about that because you're not by design a hardware designer, right? You kind of have to be these things.
Exactly. Yeah. That's my next question to Nyan. So, like, targeting a lot of embedded ML networks on the FPGA. How has been the experience?
Yeah, I mean, I think I said something like, any application is better than no application, and so sometimes having something that's a little bit more simplified makes it more accessible to users is actually super powerful, and then it gets people kind of hooked. It's a gateway, and then you get started. That's how I got started with Flutter. So yeah, I mean, like the high level language is super great. We were exploring things that make it even more domain specific and high level. But yeah, I mean, actually, I was listening to this discussion and I was thinking, everyone is like, oh, I need this one thing and that one thing, but like from the global point of view, how are the specifications and requirements in different parts defined? Maybe like having a workshop like this where so many different people are together and can lay them out, you kind of match them, and it actually makes things a little bit more organized. Yeah, I mean, we just spend most of our time trying to make things look less like an FPGA, the FPGA tools for everybody else.
At this point, it's a woolly mammoth, right? It's a woolly mammoth on an elephant.
They should just rename this conference to like FPGA Tool Bashing Conference. I've been here, I think, 3 or 4 years. Every year, every panel you go, that is the theme. The panel concludes to this point. Okay, we need better tools. Tools are trash. I mean, we have to give that to the vendors too. Like, it's a lot of work to build these tools, and all of us use them too, right? It's like, they can do immense, interesting stuff as well. So probably just the other side bringing that up. Yeah.
And assuming, let's say, the tool works, so are we limited? Like, for example, let's say tools work, right? And you have these domains, then is it that GPUs would still be competitive, right? Like, what do we do in the architecture, let's say, to compete with GPU? Let's imagine the tools. Okay.
And you win, right? Like, I mean, we've shown so many papers over many decades, like it's 10x, it's 100x better on FPGAs than GPUs. Right? But why is NVIDIA a huge company? Because they have a big infrastructure that allows people to fairly grab that, right? And I think that's the challenge. I mean, and your point is a great one. Like, these are not easy devices to program, right? We're not a bunch of idiots that are just like, how do we program these? These are hard things to program, right? And that's why you get really good performance out of them. But and that's why the tools are great, right, as well. So, but I think 100% you win. That's why maybe everybody is arguing for this sort of stuff. It's like, if you can get this to work, then it's going to be, we're going to be I don't know how big the GPU conferences are, but we're going to be one of those, right? We're not going to be, we'll be across the street, or we'll be, I don't know, we'll be in San Francisco on Skype, right? Like it's going to be a huge thing once that happens.
So basically, if I rephrase what you're saying, imagine right now we are having so many troubles with tools because they have to support so many devices, so many different domains. What if we go towards building these domain-specific tools like Chris was telling, right? For embedded AI or networking, text analytics. Is there a possibility of building these domain-specific tools and kind of not having the pain points that we usually get? Chris, do you want to take that?
Well, I think it's hard because building tools for modern FPGAs is an extremely heavy lift, right? I mean, I know we all complain about it, it's difficult, but those guys are working hard. I mean, I know it seems like it's simple, but it's a massive lift. And just, satisfying bare minimum for the broad spectrum is the challenge. So I think, this is where, I think open source tooling, opening it up to the community, giving people control over their destiny and how those designs get compiled is empowering. I think that's where we can take advantage of just domain specific characteristics and get that population and squeeze out that extra performance. If you solve that problem, no matter how fast you file above, bottom team, if you've got an open source project, you can go in there and fix it yourself, right? If it's in their critical path, you go fix it. You file it, you try it, you will keep going. And so that I think open source is really a key ability to enable to raise this impact.
Thanks, Chris. Any other questions from audience?
So one of the things that we discussed in the earlier one of the magic points that FPGA reconfiguration. If we're opening up the architecture, what does partial reconfiguration like? Such that you can do input data driven selection and modification. What does it look like to have real time into the partial reconfiguration? I think in the AI space that would be really cool to have different partial fit streams from the bottom. That's enough. Just swap it in and out. That's also mostly these are mistakes. There's some big stuff now. That's it.
I think it's a huge potential there, right? Especially in these streaming dynamic systems, right? Whether it's a car or an experiment, right? These things are changing all the time. It's being able to swap out different parts of the processing. That's been the autonomous this of having this architecture.
So having worked with some of the physicists beyond as well, it's just been awesome. They're looking for anomalies and things like that. So if you could see something and then zoom in on it at 40 million times a second, right? At that rate, like there could be some pretty big advances that. I think the challenge has always been like just with the tools, but that stuff has been an issue, right? Like reconfiguration that has been right off. Right? It's a hard thing to just totally open up and let anybody rechange the fabric. The evaporate stuff is a huge step towards that. So kudos on that effort. And I think also just kudos on those people and companies that are doing open source stuff as well. I think that's quite good. I agree. That's going to make a difference for us.
Yeah. So I was speaking about the HPC side. It's interesting that you're talking about the FPGAs versus GPUs. And obviously it's quite an sort of thing where we're going to replace GPUs with FPGAs, but is there also an opportunity for these things to coexist? Maybe FPGAs do rather than GPUs as students? I think that's definitely true. That's why I think there's a lot of focus into things like processes with GPUs position and something just make clarity with the development. So that's definitely an option. I think also domains like in informatics where in representations, operations, form data using this with FPGAs and GPUs. I think the thing that could drive GPU adoption in HPC that they're hearing is sort of energy efficiency. Because I mean, years ago I had this idea that we should really work how to model climate change without causing it. Because so all this massive compute on climate change on very, very inefficient hardware. And I think there is that could be there. But it's not going to happen until those domain experts feel that they can really leverage this as a platform and scale up and scale out, etc. Which is crucial. In fact, so our colleagues run the Golden Bell Prize this year at C, and a lot of their work was around exploiting mixed precision in planning. So and this is all on GPUs. So these are things that should be in our wheelhouse. That GPUs are slowly sort of eating away at the areas that we want to be able to make. And a lot of their work was I would argue it's even possible on GPUs and not FPGAs because what they were doing was the different stages of computations for different blocks. They were applying mixed precision, which on an FPGA we can't really quite do. But this touches up actually back on the question of PR and reconfiguration because there are levels of this. PR is something I've worked with for over a decade now. And there's PR sort of at the level of replacing bitstream, but inside the FPGAs we also have primitives that have configurability, dynamic configurability, like the DSP blocks. But there is not a single official flow from Xilinx that will take advantage of even that level of easy configurability. The fact that you can change your in-mode upload in-mode dynamically at runtime and do different operations. There is no official flow from Xilinx that exploits it. After I have that experience, it's DSP48B1, it's at least a decade. So I feel that the issue we have is realizing that RTL is not the abstraction. HLS tools are great because they sort of raise the level of abstraction for the data for the input, but they still spit out RTL. Right? And there's a lot of consideration for things that you could do in the architecture that need to be there. This is why we need ELD and pilot people as well to talk to how best to build an abstraction that sits in the middle that allows that even that level of reconfiguration of SRL outputs and things like that no tool does. You can do it as a RTL designer who knows how to instantiate primitives, but no other thing will take advantage of that flexibility. And even that isn't needed. So forget the RTL is an issue.
Cheerleader or things. So I just want to have a second concentrate. Right. So just PR first and the idea that so I use Sickle. Okay, not your Sickle, think OpenCL. Okay. PR work inside Sickle. If you invoke, you launch a kernel, the kernel is loaded, it just runs. If you launch a kernel, it's not there. But it's some other string. The one that's just in low PR to bring back. So if you want to use PR, you can use it without understanding anything about what's happening. Right? So that's kind of so I think so a lot of this and we learn to use it. And the other thing and once you get there, so we're building our own runtime system. There's certain environment where you can part of your program, you can actually look at
put loads on the string. And if the string, you can detect a condition, and based on that, launch, change the kernel, or launch kernel onto another FPGA. Right? So these kind of things you can actually do all within an ARC. You can certainly do it in RTL. It's very painful. I agree. I've been doing it that way for a long time. Nowadays, it is, things that's not a good point. It's not beautiful, but you can do it. And one last thing I'll point out is kind of figuring out about the material things. So PR today is definitely sub-seconds. And it's hard to get below 10 milliseconds. But if you build 10 milliseconds to a second, and that can be very, very useful. And you just always have to be on the edge. Because we have lots of resources. You can actually you can allocate ahead of time. Deep bench. And then so there's here we find ways to do this. There's a lot of architectures and scheduling you can do today and very useful. And also if you become very, very valuable to be down to single mills. It is about one, it can't go down to one. But I think down to a millisecond, that's the very least.
We'll take one last question and then
Yeah, I just have, I think all this I've been playing with like AI and AI. So what we found is it's just it's very different from FPGA, but I think the itself is like different. I don't even know if I should consider that as an FPGA. So that's the first one. The second one is really so with it was a PL with the FPGA fabric and AI engine. So what's the thought process and how to use them very efficiently? Because my understanding is that it basically use a different clock cycle, set the clock speed and all these things. The last question is well, the AI itself is individual product. Or you having that directly connected to high bandwidth array, even in the future to scientific related.
That certainly sounds like a good idea. I don't know if we're going to do it or not, but that sounds like a great idea. With the AI engines right there, we made processors and actually we just open source an application that lets you run LLMs on that and run a chatbot using running essentially it doesn't have to be a FPGA, but it can. But on the other hand, the FPGAs that have the FPGAs that lots of things. I don't know. Does that answer your question?
Of course, it answered the question. It's just I think this is not just a question from me. It's from many people that what do you plan to do with it?
I mean, I think it's up to the community to figure out what they want to do. Right? These are general purpose devices. We've played around with sort of the physics space bit. So they're a higher level of abstraction, so they're easier to program, generally speaking. Say FPGAs, because they're not at the logic level, so CGR level, but the processors themselves are very easy to write a kernel from a processor. Now, the big challenge that you have is the data movement within the levels and into the device. That's been talked about a lot today. It's just a bit of a challenge, right? A lot of that's just AXI stuff. AXI stuff is, that's hardware. That's hardware level things, right? So you really have to be, in some sense, again, a hardware designer to think about that kind of stuff. So I always, and they hate, I like saying, hates when I say this, but like, I think of it somewhere in between a GPU and a FPGA, since that it's a little more abstract, but it's still hard to program, right? Because the GPUs are still a lot easier to program. So you don't have to think about data movement as much as GPUs, and stuff just works. So I think it's this really nice. It's going. Everybody's excited. A lot of people are excited. Sure, see that here, but it's going to be a lot of, and I know Indeed's spending a lot of people, probably some people working on this, trying to get stuff. And Drew, I don't know if Drew's still here, but doing awesome work on that stuff as well. but I think at the end of the day, it's going to be a little bit difficult to get just even on the AI engine itself, but then, like you say, from PL into AI, just there's a lot of interesting stuff that's being done, can be done there, but all that is really bespoke right now. We'll get some good research on this.
Thank you, everybody. I think it was, 2 minutes left. So little closing statements, maybe a feature that you think you want for your domain in the FPGAs or something in the CAD tools that you want. Just 30 seconds, everybody. Go for it.
Oh, yeah. Sure.
I think I do like to see focus on speed of actions. We got to mention this earlier. We were 24-hour file cycles. That's fun. A bunch of them in parallel because the also but CGUs are not something.
I think fundamentally, hierarchical structured flow from top to bottom just describe everything else. And I like sometimes just ask the question, how many times has the 32 bit adder replaced the original hours and wasting
we do it more very specific in beyond what we can see today is here. If you think about some more SOC and some characters, even have a COD, the architecture, if it's given value, it's going to change. Actually, architecture or FPGA technology is everywhere in SOC, just because we don't know we have. And with the technology, we can sell that data to the SOC to the very useful architecture and optimize. And with open source knowledge, we discuss can really help you to print and convince this compiler. Very efficient, prices about making a content, and anything or something that size that costs a lot. And it's also a technology has support the first type function of DLFG. I think that's a relation of more.
I think my kind of takeaway, the point that I want to make is if I made an argument in my presentation that open source is good for security. And if open source can be good for security, I feel like it should be good for all domains. I think that's something that we should really continue to nourish and support.
Sounds what you might do. I brought it up. I really, what you said really resonated with me. Open source. Maybe one step further than that is how support open source. That I feel is just saying let's have open source stuff, and then I go to some repos. This is awesome, and it's been stale for 3 years, and there's no documentation, and that doesn't mean so. How do we actually support it? That's a real maybe goal.
All right. Let's give a round of applause for all of our panelists. Thank you so much for attending. I know we are a little bit over time. I have 2 closing slides here. We will post the slides. We have gotten the slides, most of them from the presenters and the panelists, so we'll post them on our website. And we do have a survey just to get feedback from you guys on how you felt about this workshop. We do plan to have more iterations of this in the future. How can we improve it? What more sessions or what more parts that you would like to see? Please provide feedback. That's it. Thank you so much.
Thanks for having me. This was awesome.